Tokunaga. He grew up here on Maui, graduated from Baldwin High School. So any alumni out there that want to? No, okay.
Go Bears.
Yeah. He got his degree in infrared astronomy from the State University of New York at Stony Brook. Staff astronomer for the Infrared Telescope facility. Since then, he's become the director of the IRTF and has been director since 2000, which it's been a very productive instrument since then. He's very well published. His focus is on instrumentation, star formation, and planetary science, as well as telescopes of all sizes. And so let's give a nice Maui welcome to our own homegrown. And so, I can wear this? Yes. Yeah, you get to wear that. You get to wear it. Try flipping around the other way. That should be a little better. And then do a little sound check with.
Check. Check. Can you hear me? Okay.
Yeah. Okay. And when they ask questions at the end, if you repeat them, that way people in the audience, in the remote audience can hear.
Yeah.
All right. I will remind you.
Is this correct? It's not correct.
Yes, it will.
So I'll get this sorted out here. Okay, that's better. Okay. Well, I got interested in astronomy in high school and went as far east as I could to New York State to get my PhD. And then one thing led to another, and here I am. This is a picture of the NASA Infrared Telescope facility at Mauna Kea, and I came to the Institute for Astronomy as a staff member for this telescope in 1980, and have been here ever since, and now I'm the director of the telescope.
How big is that one?
It's a 3-meter aperture, yeah. And now it's considered a small telescope. In fact, one of the telescopes we'll be talking about later in the talk is the 30-meter telescope. And the secondary mirror of that telescope is about 3 meters. Okay. So it's mind-boggling how big, how much things have progressed. In this talk, I thought I would start off talking about the importance of small telescopes. The big telescopes tend to get all of the publicity, and there's a lot of money involved, and people get all excited about it. But there's actually a lot of very interesting and significant work being done with smaller aperture telescopes. And I'll talk about I'll give you some examples. They're mentioned up here, the UH 2.2 meter telescope, exoplanet search telescopes. And also, recently in the past 5 or 6 years, there have been more and more work being done with networks of telescopes, maybe up to about a dozen telescopes in different sites, observing simultaneously. And the Las Cambras Observatory is one example. And there's a telescope at Haleakala, which is part of this network. I guess you must be working with that telescope. There might be some people here working with that telescope. Yeah. Yeah. I'll also talk about the NASA Infrared Telescope facility, what we do, and some studies we're doing with near-Earth objects. And this ties in with the Pan-STARRS telescope at Haleakala, which are searching for these near-Earth objects, and we can make physical observations and learn a lot about the composition and size of these objects. And then finally, I'll end with some thoughts on the growth of telescope aperture, and maybe stimulate some thinking about, is there a limit? Can we, make ever larger and larger telescopes? Is there some limit? The answer is we don't know, actually. But basically, funding will determine how big we can make a telescope. Okay, well, what's the future of small telescopes, quote unquote. In the United States, we have a tremendous number of facilities that would be considered modest aperture or small telescopes these days, below, say 3 or 4 meters and below in aperture. There's a lot of acronyms here, but some of the ones that are relevant in Hawaii is the IRTF on Mauna Kea, the UH 2.2 meter telescope at Mauna Kea, the EOS telescope at Haleakala, the Canada-France-Hawaii telescope at Mauna Kea, and there's the Las Converse Observatory again, with one telescope at Haleakala. There's also Pan-STARRS and other survey telescopes. And these survey telescopes are making a huge impact on astronomy and leading to ideas of having a virtual observatory where all the data is archived and you go to this big archive and basically do your observations in the archive. There's also been some discussion about, I read a paper on using tools like Second Life to visualize data. So you can walk into the data set, look around, and try to make connections between different sets of data that would be difficult to visualize in any other way. Basically walk in, step into the data, become part of the data. These are just thoughts. I don't know of anyone who's actually done it, but I thought it's interesting because there are people out there in Second Life, I guess, watching this talk right now. Okay, I want to talk about some of the discoveries made by small telescopes. One is the discovery of the Kuiper belt. This is small cometary bodies that are outside the orbit of Neptune. The first one was discovered in 1992 on the 2.2 meter telescope in Mauna Kea, by researchers at the University of Hawaii. And this really opened up a whole new research area. Oh, I can use this, sorry. And people went out looking for more of these objects, and now there's several thousands discovered.
Are those real images?
Oh no, this is artist's conception of these bodies. So the only thing that's significant is the diameter of the bodies. So it gives you some idea of the range of the bodies.
There's been no flybys yet on any of the
No,
objects.
no, but there is one that's just about to happen. In 2015, a spacecraft will fly by Pluto. And Pluto is the largest body that's in this class of objects.
Call it a Kuiper belt object now?
You can call it a you can call it a dwarf planet or a Kuiper belt object, or you can even call it a planet. I mean, no one will put you in jail for it. Yeah.
I would like it.
Yeah, some people are still unhappy that Pluto is no longer formally a planet in the eyes of the International Astronomical Union, but it's just a definition. Of course, Pluto is oblivious to all of this. It's what it is, and it's very happy. Yeah, so it's not offended by what we think, what we call it. Yeah. But these bodies are able to tell us quite a bit about what's out in the outer solar system and how the solar system formed. There's some seats here if you want to try and get in. Okay, so this is somewhat a busy plot, but it's plotting two things. One is the orbital inclination, so how much it's tilted relative to the major planets. Oh, that's nicer. And the other thing it's plotting is the distance from the sun. So Pluto is right here in this plot. So it's at about a distance of about 40 astronomical units from the sun. and at an inclination of about 20 degrees. So its orbit is tilted relative to the other major planets like Saturn, Uranus, and Neptune. And that's one indication that this was not quite a typical planet. But now we know that there are thousands, hundreds of thousands of objects out there with orbits that are characteristic of the type of orbit that Pluto has. And you can also see a clustering of objects here at near 40 AU, and each object has a different inclination, and they show up as a clustered together in this fashion, and that's because they're in a resonance with Neptune. So every 2 times that Pluto goes around the Sun, Neptune goes around 3 times. And so there is a gravitational interaction that reinforces itself, and that causes the planets to migrate to this region in this plot. And so we know that Pluto is one of many objects that fall in this gravitational resonance.
Is there much commonality of the eccentricities of the orbits as well as the inclination?
Well, you can see some regularities in this plot, right? You can.
Yeah, I see that.
Yeah.
But I'm talking about the eccentricity of the orbit.
Is there any regularity in eccentricity?
Is there any commonality? Do they all pretty much have low inclinations, or?
No, there's quite a variety. See, they like in this group here.
Of eccentricities, I meant, not
Yeah.
inclinations.
Let's see.
No.
I'm not plotting the eccentricity. I'm not aware of any correlation with eccentricity and the orbit.
Another plot.
Yeah.
Another axis,
Yeah. Right. So that question was about how elliptical the orbit is, and some of these are very elliptical orbits, and not very circular.
It's got some resonance with something too, doesn't it?
What's that?
The Kuiper looks like it's got a resonance. The blue plot. They're pretty well clustered.
Yeah, you have to be careful. There's some observational bias, but you can see in this group of blue objects, there's some that show correspondence with the resonance with Neptune. There are these linear features here in red.
Yeah.
Mm. But anyway, this has opened up a lot of theoretical and observational research into the origin of the solar system and how the bodies interacted and formed larger bodies like the outer planets and also the Earth.
What's the reason for the Kuiper belt? Why are so many particles there?
Oops. Why are there so many out there? They're just the remnants of the...
Why there? Why not scattered homogeneously throughout the whole solar system? I mean, obviously there's some resonance going on to bunch them up at that particular orbit. I think it cleaned up like collision.
I mean, why aren't they closer in? Or, yeah, actually, we can save that for the question and answer period. Okay. Okay, another discovery made by a small telescope was the existence of transiting planets. In hindsight, it's not surprising that they exist. But the first one was discovered using a 4-inch telescope in 1999.
It's huge. Look at it.
Yeah, oops. Yeah, this is showing a dip in the flux of the star by about 2%, and nowadays that's considered a huge
And it's so
signal.
amazing that it was discovered with a 4-inch scope. I mean, nobody would,
Yeah,
even the seeing would have washed it out. Most
Yeah.
people would think, but there it is.
and later a spacecraft was space telescope was launched called Kepler, and they discovered many transiting events, and a very interesting result. The goal was to find Earth-sized planets, and determine how many there are and the distribution. And recently a result came out indicating that about, up to 1/5 of stars in our galaxy have an Earth-sized planet. And so it comes out to be about 40 billion possible Earth-sized planets in our galaxy. Well, Kepler has found some of them, actually, a few.
I mean, in the Fermi state. This is point of view.
Another example of the use of small telescopes is occultation work. This is showing an event where Pluto went in front of a star. It's called an occultation, and depending on where you are on the Earth, you will cut the star will cut across Pluto at different distances from the center of Pluto. So these horizontal dash lines indicates the path of the star across Pluto from a place on the Earth, and it's indicating different places on the Earth where there were telescopes to observe this event. So what you get is a series of light curves from the different places on the Earth, which correspond to different cuts across Pluto. And then from that you can get some idea of the shape of Pluto. Well, Pluto is spherical, but if it were irregular, observations like this could tell you how irregular the object is.
Might you show something about any observation in the atmosphere as well? If you have a big enough telescope, you can look at a spectrogram of the stars.
Yeah, that's right. If you have enough signal to noise, you can say something about the atmosphere. And for example, the AAT, which is a 4-meter telescope, it's not so clear here, but when you blow this light curve up, there is information on the atmosphere of Pluto.
It's a lot less noisy than the others.
Yeah, because the others are smaller telescopes.
And of course, if that star had an orbiting planet, you'd, in theory, be able to see a little irregularity in the light curve on that, provided the seeing was good enough. I don't know how many arc seconds.
Yeah.
Talk about that at the end.
We can. If it had a satellite, it might be possible to. Heck, Pluto does have a satellite.
No, I mean the star had a satellite of a planet.
That's right. Yeah.
Curious.
Okay, there are many other examples of small telescopes that are doing significant work. One telescope, 2MASS in particular, it's already stopped observing, but it was one of the first modern infrared sky surveys. The Sloan Digital Sky Survey is another famous survey at optical wavelengths. And pan-stars in time may achieve the same amount of what's the right word? Notoriety. They're just beginning to get really nice results out with pan-stars. So we can see the increase in publications rising rapidly. So small telescopes are indeed making significant discoveries. There are networks of telescopes like Las Cambras that are providing a new way to do science. And so I think that, and also sky surveys will have a big impact on future research. Now at the IFA Maui, Jeff Kuhn and his collaborators have been also interested in small telescopes. They've built a half-meter solar telescope, and they're trying to get the funding and parts together for a 1.8-meter telescope for it's for is this exoplanet transits?
The Japanese are interested in these planetary problems too.
Yeah.
These small telescopes have a great feature. In fact,
Mhm.
you can make them so that they're optimized not just because they have a big mirror, but so that you can see faint things next to bright things. So there's
Mhm.
another dimension to what you're saying, which
Yeah.
is something that can happen with small telescopes.
Oh, that's right. It's a high contrast telescope for
Low scatter.
yeah. Right.
Impossible.
And the great thing about small telescopes is that a relatively small group can put something together and make great discoveries. Okay, now I'm going to spend some time talking about the NASA Infrared Telescope facility. So here's a picture of the observatory. It's kind of a unusual design, having a building that's kind of like a box with a dome on it.
Can we turn off the backlights? Is there any reason for them to be on?
Yeah, that's better. And this telescope is operated by the University of Hawaii under a cooperative agreement from NASA. So it started operations in 1979, and its main purpose is to provide mission support and an observing resource for the planetary astronomy program at NASA. And the value to NASA, the value to NASA is that.
They can't see the speaker. Sorry.
Oh.
Well, does he need to be seen? He's just talking. Let's switch it on. Keep you awake. Well, I think that, okay.
The value to NASA is that this telescope can respond quickly to events. The instruments are optimized for solar system research. We employ flexible scheduling, which means you don't have to observe for the whole night. You can request 1 hour or 2 hours during the night. And also you can request, like say, 2 hours every month for 6 months. And we can schedule the telescope in that way. And it's accessible to the entire community. And I'm stating it this way because most of our observers do not come to Hawaii to observe. They observe from their office or their home or wherever they happen to be. People have observed from the hotel room when they're on travel. It's amazing how flexible and how much it opens up observations with this telescope.
And you can fit different instruments on the telescope.
Yes, yeah.
Within 1 hour, you can change from a spectroscope to a
Yeah.
fancy camera.
Yeah, I'll show you a picture of that. Yeah. And this is a picture of the telescope when it's got some snow. Yeah, this is, oops, keep pressing the wrong button. This is the IRTF. It's a 3-meter telescope. This is the Canada France Hawaii telescope. It's a 3.6 meter. And this is the Gemini telescope. It's 8 meters. So from the right perspective, you know, we look okay. Yeah, but I don't have any aperture envy, so I've gotten over it. Yeah. That doesn't bother me anymore. Maybe you can turn off the lights again. Just. So this is the business end of the telescope. Oops, keep doing that. Right here.
Is it altazimuth mount?
No, it's an equatorial mount. It's hard to see, but we have I think it's called an English mount. So it's got a big. It's not a horseshoe. It's an open structure, and the telescope. It's a yoke, actually. Yeah, telescope can move north and south in the yoke.
Sort of like the Mount Wilson telescope, the 100-inch.
Um,
No, it's not in the yoke. That's not in the yoke.
Yeah.
The yoke is like a fork.
Yeah, I don't recall what the 100-inch looks like, but anyway, it's got a yoke mount, and the I think most of you are familiar with this, but let me mention it anyway. The primary mirror is here, and the light is collected by the primary mirror, sent to the secondary mirror up here, which you can't see, and is brought to a focus behind the primary mirror in this area where the instruments are located. So it's heavily instrumented. And we don't even have an eyepiece. So I couldn't, if you came to the telescope, I couldn't have you take a look through it. You know.
Are there switching mirrors to move the light back and forth between the packages?
Yeah, we can not switch the light, but we can switch the instrument. So there are 4 instruments typically in the back here, and we can switch.
Will you translate them into position?
It's like a switch yard, so
Beam switch.
we can move one instrument out from the center position and put another one in, and we can do that within 30 minutes. So during the night, we can make one or two instrument changes to accommodate the observations, and that gives us more flexibility. This slide is to just illustrate various missions that are going on right now, and we have proposals to use the IRTF to support these missions. And so we have the Mars Reconnaissance Orbiter, Mars Exploration Rovers, New Horizons, which is a spacecraft that will go fly by Pluto in 2015. Spacecraft called Dawn, which just visited Vesta and is on the way to Ceres. Cassini, which is in orbit around Saturn. And Juno, which is on the way to Jupiter. Unfortunately, the number of missions that NASA can afford to support has gone down. So in the future, this chart will look a little sparser. Now, one of the things that was discovered on the IRTF, although it's somewhat controversial at the moment, is the detection of methane in the atmosphere of Mars. And what's shown here is a spectrum at a wavelength of about 3.3 microns. And the top spectrum shows the spectrum of the Earth. So this is, you can see bands which arise from water and methane absorption in the Earth's atmosphere. And there are various spectra of Mars shown below at different latitudes across Mars. And I'll just illustrate one case at the top here. There's a small absorption feature in the spectrum of Mars, which is close to the telluric methane absorption, but it's slightly shifted because of the motion of Mars relative to the Earth. That shifts the line. And so the methane line on Mars is on the edge of the methane line on the Earth, and this spectrum shows the extraction of the signal from Mars, where you can see the absorption from methane on Mars.
That's a transmission spectrogram, am I right?
It's in transmission, yeah.
And what you're using the radiation from the planet's surface itself, and that's what the source is?
Yeah, we're at thermal wavelength, so
Okay,
we're
so
looking
that's
at
the temperature of Mars. Okay.
it's the emission from the surface of Mars, and we're seeing the absorption in the atmosphere. Oops. Because we have spatial resolution on Mars, we can see what the distribution of methane is across the disk of Mars, and there's evidence that it's concentrated in certain areas on Mars. So the conclusions are that the abundance is not uniform. Few observations after this were not able to detect methane on Mars, okay? And this is where the controversy comes in. Okay?
Nothing left at all? Nothing to
That's right. Yeah. So if the initial observation is correct, then the methane is destroyed in less than 1 to 3 years. But that's not considered probable in the eyes of people who do the chemistry of the Martian atmosphere.
Those look like nice, strong absorption.
Yes, they look very convincing. But this kind of thing happens in science sometimes.
Could it be rocket exhaust? When they have
Yeah.
a lander, a lot of stuff kicked up in the atmosphere. Maybe
No, it requires too much methane for that.
not
Yeah.
enough. Tons and tons.
Yeah. Now, people are still actively searching for evidence for methane on Mars. For the observation to be correct, there was enough methane to be seen from the Earth, so there had to be some kind of outgassing event. So something belched on Mars, and yeah. And the second thing is that there has to be some process that destroys Mars much faster than what the theoretical models would suggest. Yeah.
That's fairly high resolution, that picture you have. That's superimposed over an orbiter picture, I take it.
No, this is showing a false color image of the distribution of methane on Mars as observed.
But the image underneath is a green background. Yeah, that's from an orbiter of some sort, I presume.
Oh yeah, there's some yeah.
It's definitely not from a telescope.
Right. Yeah, that's right. Yeah.
Ain't that good yet?
Yeah. Okay. Well, anyway, that observation generated a lot of interest, and there's active observations going on to confirm the detection, and maybe it'll turn out to be one of these things where the initial observation is incorrect.
But it was localized. That's the amazing thing. I mean,
Yeah.
that one's correct. It wasn't
Yeah.
just methane in the general field of view. It was pinpointed in very.
Yeah, that's right. Yeah. Okay. Now another topic I wanted to talk about is studies of near-Earth objects. Some of you might remember this famous object. It's a near-Earth object called Apophis, which came very close to the Earth in 2004. And the scary thing is that in 2029 it's going to come very close to the Earth again, 5.6 Earth radii. And for some time, it was unclear whether it would hit the Earth or not. Now we're pretty sure that it will not hit the Earth.
Sorry, could you clarify pretty sure?
It's extremely unlikely. So I don't know what the probability is, but it's near zero. Okay.
That means you established a pretty stable orbit for it, which I presume means that perturbing influences between now and 2029 have all been taken into account, like where Jupiter is, for instance.
They think they can calculate all that. Yeah.
So all
Yeah.
the big things have been.
Yeah. Yeah. But it has a fairly short orbit. So let's see, it's about 25 years. So every 25 years, this thing is going to come close to the Earth. So there is a worry that someday it will decide to hit the Earth. Yeah?
What about coronal mass ejections? Is that something they take account for in perturbing the orbit, or is that not big enough to worry about?
I don't think that's going to be big enough. Yeah. Well, this object was not discovered by the IRTF. It was discovered by another telescope, but at the IRTF we were able to get an estimate of the size. It's about 300 meters. So that's enough to create significant damage if it did hit the Earth. And the Pan-STARRS telescope is actively looking for more objects like this, in particular the ones that come close to the Earth. And we have, at the IRTF, we can react quickly. So within 24 or 48 hours, we can change the schedule and make observations of any near-Earth object that is of interest to NASA or that might be a danger to the Earth. So we're kind of on standby. There's a target of opportunity proposal whenever the principal investigator thinks there's an interesting object that we should make physical observations of. We'll break off the observations and the scheduled observations and take a look at it. And also there's another small telescope project called Atlas that is just starting at the Institute for Astronomy. And Atlas is a half meter telescope that will try to discover objects that are headed toward the Earth. And the PI estimates that there can be up to about a week of advance notice. which isn't much time to go hide somewhere, but yeah.
The Russian meteorite, did people look backwards and see if anybody actually had it in their field of view?
No, nobody saw it coming.
Can you please repeat all the questions so that the audience...
Okay. Yeah, sorry. Yeah. He asked about whether the meteorite from Russia was seen before it hit the Earth, and the answer is no. Nobody.
In retrospect, though, did they go back
No,
to the records?
nobody saw it because it came in the direction of the sun. Yeah. And it's small enough that it would not have been picked up by the survey telescopes. I've asked it's amusing to think about what might happen if the Atlas PI, John Tonry, found an object that was headed toward the Earth. He was guaranteed to hit the Earth, and was large enough to devastate everything, all life on the Earth. And I asked him, well, what would you do? Would you let people know, or or not? I mean, it raises some interesting questions about maybe ethical questions about how we should react to events like this. If there's nothing we can do about it, is it better not to know? Yeah.
I think in the name of science, it was certainly nice to observe it from orbit, and so that the films on that particular satellite, if they're ever discovered afterwards, would be an event that they could look at. I mean, it's low probability, but I think it would certainly be an interesting piece of data for people who found that satellite if it was in such a position where they could retrieve it.
So just record everything.
Well, yeah, if you know you're going to be all destroyed, at least you have a for posterity for those who might visit the Earth.
What was their answer? Did they tell you yes or no? They tell you.
No, he kind of went like this, and I didn't get a clear answer.
You calculate where it would land, and then you get a plane right to the exact opposite area place on Earth, and then you would tell people.
Yeah.
Can we hold questions to the end? I'm
Yeah.
getting comments from internet audience that they're being left out of the discussion.
Yeah.
So.
Yeah. Okay. Let's see. I should speed up a little bit. So I want to talk about Titan, and I'll try to go a little faster. Titan is my favorite place in the solar system. It was explored very extensively by the Cassini spacecraft, and also the lander, which is shown here, this gold disk here, that went into the atmosphere of Titan and landed on the surface, which is just incredible. So if you take a visible light photograph, you get something like this. Titan is covered in a lot of haze. The atmosphere has a lot of haze, so you can't really see the surface at optical wavelengths. But if you take a very narrow band image of Titan, where the absorption in methane is not so great, you can see down to the surface. So here it's possible to see some surface features on Titan. And here's a nicer image of the surface features on Titan. It looks like there might be an ocean here, but it's not. It's just dark material. Yeah. And there are some clouds here that are high altitude. They stand out more than normal.
Do you know what wavelength that image was taken at?
I don't know the exact wavelength, but it's a narrowband image, and probably at a longer wavelength, about 0.9, let's say 900 nanometers or something. Now, these clouds can be observed from the ground. These are some adaptive optics images from Keck, and you can see the bright spot here at the bottom, which are the clouds, and also some smaller cloud features like here. But it's not always like that. Here's a set of images from from 2004 and 2008 where they just did not see anything. So it's highly variable.
Telescope was working well.
Yes. And this is consistent with data that was taken by the IRTF at that time. We have a program to look at the cloud coverage on Titan, and they do this by looking at how much signal there is in the center of a very deep methane band in the infrared, and the clouds, which are very at high altitudes, will present a signal. So this plot is showing that it's near close to zero. There's some fluctuations, but it's very close to zero. And if there were a cloud, the signal would be up here somewhere.
And inclination and orbit,
Yeah.
those aren't seasonal, are they? Something to get out?
No, not seasonal. But maybe we can wait until the end to discuss that more. And then all of a sudden there was a big spike in the signal. So here it is. And so what they did was to request time on the Gemini Telescope to look at Titan. And they found it had a very bright cloud. Yeah. So this is an example where the IRTF was used to monitor Titan, to look for cloud activity, and then use a larger telescope with adaptive optics to image Titan and see where the cloud is and how large it is. Yeah. And the Titan flybys at the time missed this completely. So now I'm going to digress a little bit and just talk a little bit about Titan, because it is really fascinating. So the lander on the Cassini spacecraft reached the surface, and on the way into the surface, it took pictures. And here's a picture from the lander looking down at the surface. And if I didn't tell you this was Titan, you might say, "Wow, okay, it looks like a river and very terrestrial looking."
River Caroline.
And this is what the surface looked like from the lander. And if I didn't tell you anything else about this picture, you might say, "Wow, it looks a little smoggy." And there's some rocks here, but these are not rocks. These are blocks of ice, yeah? Water ice. And the reddish material is some kind of organic compound, and it also exists in the atmosphere. And this organic compound is basically settling down on the surface all the time because of the methane in the atmosphere is being photodissociated or broken up into smaller pieces that are then recombining through chemistry and forming complex hydrocarbons. The power source for the power source for the lander was a battery, so it lasted, I think, just a few hours on the surface. Yeah.
Can we hold questions and comments till the end?
Okay, and it's interesting that the atmosphere is mostly nitrogen, and the surface pressure is 1.5 atmospheres. It's much denser than on the Earth, and the temperature is 96 Kelvin or 290 degrees Fahrenheit. So it's and at these temperatures and pressures, you can have liquid hydrocarbons, liquid ethane, and you can have precipitation by methane or ethane onto the surface, and that's what's causing that river-like structure. It's the liquid hydrocarbons carving out channels in the surface. And there is a radar on the Cassini spacecraft, and as it goes by Titan, it makes a radar map. And from the radar observations, they believe that this is a false color, so this is not really a color. It's just radar observations that have been transformed to a color scale. And the blue areas represent a certain level of reflectivity from the radar. And they interpret the observations that they have, and there are other supporting observations for this, that this is a liquid. And it's not quite, I don't think people are 100% sure if this is ethane, C2H6 liquid, or methane, CH4 liquid. I think the majority of people think it's ethane. Yeah. And you can see river-like channels. And again, if you didn't know where this radar image was taken, you might think it was somewhere on the Earth. So here's an artist's conception. Someday we may want to take a vacation here, and no, you wouldn't. It's too cold. So we'll have to leave Titan. I'm running out of time. We'll go back to the Earth and talk about more mundane things. I mentioned that we do a lot of remote observing with our telescope. So that means the observer doesn't have to go to the telescope to get the observations, and instead he or she can work at a computer workstation or laptop, and these the screens show exactly what you would see at the observatory. So it's showing the controls for the instrument and the information that comes back from the instrument, and where the telescope is pointed. And you can also move the telescope using the mouse remotely. Yeah. So, well, many observatories offer remote observing. We're a little unique in that we allow remote observing from virtually any location. Yeah. And we can schedule time slots as short as 30 minutes. And we can make instrument changes during the night. One program could use several different instruments, or we can have different programs scheduled for the night using different instruments. Okay. And this is a blow-up of what the observer sees. So we have a panel that shows the instrument control, a panel that shows the data coming out, another panel that shows where the telescope is pointed, and also we have controls for moving the telescope. And we have a picture of the telescope operator. So there's two-way communication. Usually they will use Skype, but we also have the Polycom. And it's not really necessary to use Skype. We can use just a conference phone. But it's good to see a human at the other end of the line. So actually this image, it's hard to see, but this image shows the telescope operator here and the observer. And one of the interesting things that I didn't think about when we started remote observing is that, but it happened very naturally, and it's very good, is that people in different locations can work together remotely. So we can, for example, a program might have 2 or 3 investigators. One could be in Boulder, one could be in Flagstaff, another could be in Tucson, Arizona, and they can all log in and agree. You know, first have to agree on who's actually running the observations. But once they decide that, they can all interact. They can see what's happening. They can, in real time, they can have discussions about how long to continue the observations and so on. This shows the different locations as of last year. So we have people, remote observers in North America, South America, Europe, Japan, and Korea. Okay, so now I'd like to switch gears to the topic of large telescopes. I don't have time to talk about how they're constructed, although that's very interesting. I'm going to focus on the evolution of to larger and larger telescopes, and what this means for the future. I'm not sure entirely myself, but and I think it is interesting to ask: is there a limit to how large telescopes will get? Now, this picture. Sorry, let me back up a little bit. This picture is showing the two Keck telescopes at Mauna Kea. They're each 10 meters in diameter. And there are plans now to build a 30-meter telescope at Mauna Kea. And just for comparison, this shows how large that observatory will be in comparison to the two Keck observatories. And the secondary mirror, which you can sort of see here, yeah, that's about 3 meters in diameter. Yeah. Well, maybe I do have aperture envy after all. I'm not sure. Okay, well, if you look at the growth of telescope aperture, this is what you get. Now, this is a simplified plot. I'm sort of showing the upper envelope of telescope aperture with time. So we start here in 1609 when Galileo built. He did not build the first telescope, but he used he was the first one to use the telescope for astronomical observations. And you can see a replica of the telescope here. So it's been roughly 400 years since the invention of the telescope. And the aperture was 1 inch. And Newton came along later and built the first reflecting telescope in 1672. This is I think well, I'm not sure why I put this picture up, but it's one of the famous telescopes. It's built in England by Herschel. And this picture is showing the largest refracting telescope ever made, the Yerkes telescope. The lens is about 1 meter in diameter here, and that represents the technological limit, because as lenses become larger and larger, it becomes harder to support them because you have to support them on the edge. And so at some point, the materials just cannot accommodate the stresses on the edge of the lens. So if you want to have larger telescopes than 1 meter, you have to have reflecting telescopes. Now, in 1949, the Hale 5-meter telescope was constructed. And this represents the culmination of telescope building for 400 years, or maybe 350 years. This is an equatorial telescope and built with classical methods. This is one of the last telescopes built using the old recipes that go back 100 years. Yeah. After this time, people realized that new ways of building telescopes is necessary to be able to build them in a practical sense, both in terms of construction and also in funding. Yeah. So you have to find more cost-effective ways of building telescopes. Now, the Keck Observatory represents one of the major advances in telescope building. Maybe it's hard to see, but there are 36 elements that make up the telescope. It's a segmented telescope, and these elements are aligned to optical tolerance. Now, the advantage is that each mirror, there are 36 of them here, each mirror doesn't have to be as thick as if you had a single 10-meter mirror to support the weight. So that simplifies a lot of things. You can reduce the weight of the telescope and the structure. And also it uses an altitude azimuth mount. So it's built like a gun barrel. So it can go up and down in elevation, and it can move around in azimuth. So you can get to any point of the sky. And that allows, the advantage is that that allows you to build a more compact telescope, and therefore the enclosure is smaller, and that reduces the cost. Now the LBT took another approach toward increasing aperture, and they have two 8.4 meter primary mirrors that are co-mounted on a single mount. And so it is possible to combine the light from these two mirrors into as if it were a single telescope. And that's why I've shown it here as being larger than Keck, because even though the primary mirrors are 8.4 meters, when combined, the collecting area is equal to about 11.5 meters. Okay, now the interesting thing is going to be this area of the plot, okay, going into the future. If we look at the growth of telescope aperture since about 1900, you can sort of draw a straight line. And I'm kind of cheating a little bit. This is logarithmic. It's a logarithmic scale here. So these are factors of 10, and this is a linear scale. So on this kind of plot, small deviations in this direction are made to appear smaller. Okay. So it's full disclosure here. But nonetheless, it looks like a pretty good fit here. I can fit a straight line. Okay? And I can say, well, it looks like the doubling time for aperture is about 20 years, from 1900 to about 2000 and, I don't know, I guess it's about 2010. Now there are projects that appear to be real, in the sense that they have spent hundreds of millions of dollars. They have extremely sophisticated, advanced engineering drawings. They're lining up the funding, and they're thinking of building a 20-meter telescope equivalent, roughly, and a 30-meter telescope, and roughly a 40-meter telescope. I didn't have time to revise this slide, but I'll describe what these projects are. But note that if they can build the telescopes when they think they can, they're way off the curve. Okay, even though I'm cheating with a log linear plot, they're way off the curve. Okay? So a 30-meter telescope, for example, I would expect with this linear extrapolation to be built in the year 2050, roughly. Yeah? Okay, the first one is the giant Magellan telescope. This consists of 7 mirrors that are 8.4 meters in diameter. And the light from all these telescopes are combined into a single point. And I have to give credit to Jeff Kuhn. He came up with this concept for the Canada, France, Hawaii telescope a number of years ago. And as far as I can tell, Jeff, they just stole your idea. And did you ever get credit for this? Is he still there? No, oh. Oh. Oh, that's too bad. That's too bad. I would like to have known what he thinks about this. Anyway, the next large telescope is the 30-meter telescope. Oh, sorry. I should have said that this telescope is being funded by a consortium of universities in the United States, by Australia, and Korea. and they think they can get enough money to build this telescope. So they have made, fabricated, and they're polishing, maybe finished polishing one of these mirrors, but they have 3 blanks at the moment. It's hard to emphasize how difficult this project is, to make fabricate and polish a mirror of this size and its off-axis is tremendously challenging. Okay, the next largest telescope is a 30-meter telescope. This is a segmented mirror telescope like the Keck telescope. It will have about 500 segmented mirrors that will be aligned to optical tolerance. And this is a planned for being planned by a consortium involving the California Institute of Technology, the University of California, Canada, Japan, China, and India.
Is it fully funded yet?
No, none of these projects are fully funded. Yeah. But they have lined up. Oops. Sorry, technical difficulties here. They have lined up about $500 million, and I think the previous project probably has about $200 million lined up. And then the last, I'm almost finished. Oops. I can see JD is getting anxious here. But
No, actually not.
okay, running a little bit late. This is the largest telescope being planned right now is a European extremely large telescope. It used to be called the overwhelmingly large telescope. But that's when it was 100 meters. That was really very ambitious. And even this slide is out of date. It's been reduced to about, it's now the current aperture is about 39 meters. Yeah. So, you know, if you think about what limits the growth of telescope aperture, first of all, it's vision. Somebody has to have a really clever idea of how to build something larger for lower cost. There has to be technical progress. There's competition. I mean, for example, I'm showing here roughly the dates that they claim they will be operational. Yeah? And it's not an accident that they're all lined up here because nobody wants to build the second largest telescope in the world, right? Yeah. So competition is definitely important. And there's politics, and there's economics. And economics, I think, if we go back to the this plot, if you plot this on a linear scale, so if you make the vertical axis linear and the x-axis linear, then you'll see an exponential curve. Yeah? So aperture is increasing exponentially, and we know that nothing can increase exponentially forever. Yeah? So there will have to be some kind of roll-off in this plot at some time in the future. It's just not possible to make any predictions. So this is the last slide. So I claim we live in the golden age of astronomy. Yeah. Thank you. Yeah. Yeah.
Where do they hope to build those 3 large telescopes?
Yeah, I forgot to mention that. This thing doesn't want to stick on my ear for some reason.
You could just hold it in your hand.
Ah, okay. Yeah, that's better. Why didn't I think of that? The question was, where do they plan to build these large telescopes? The first one, the 20-meter equivalent aperture telescope, is planned for Chile. The 30-meter telescope is Mauna Kea, and the 40-meter telescope that the Europeans are planning is for Chile. Yeah. I beg your pardon?
Weren't you saying that the design for one of them was stolen from Jeff Cook?
Yeah, Jeff had.
The 7-mirror design.
Yeah, no, not the segmented mirror design. The
7.
no, it's the 7. Yeah, 7 mirror design arranged in circular.
Alan doesn't know about our discussion of the Colossus.
Oh, actually, now that you're here, I told the audience that this project basically stole your idea, and
Moved on. Moved on to a 77-meter telescope.
Somebody got lined up.
so Jeff, where can I put that Colossus telescope on this plot? I mean, what time?
The magic of this telescope is that it uses some of the same ideas of the GMT, so it doesn't require a stiff structure. And so we should talk about it afterwards. But there's this private group which has invested now almost $1 million in the design work for it. The same guys that built the Keck telescope, Dynamic Structures in Vancouver. And this group's belief is that it could be built for less because of the way it works than the TMT. So the magic number is 5 years. 5 years and less than, and this is the bargain, less than $1 billion. because this is a telescope that has a field of view of only 4 arcseconds, a gigaflex. And when you do that, magic things happen.
Okay, so Jeff is claiming his telescope would be is possible up here. Yeah. Yes.
How do these telescopes compare to, say, the Hubble telescope was out in space or still out there?
Yeah, how does it compare to the Hubble telescope? You're talking about these large telescopes? Yeah, they're complementary, because the Hubble telescope has let's see.
It's 2.4 meters, about 100 inches.
Yeah, most of the science I can think of are complementary. So a Hubble telescope will have a larger field of view. These large telescopes will have a smaller field of view, but they'll have more collecting area, and also much higher angular resolution. Yeah. So the science is complementary in general.
No,
Yeah.
that thing has off-axis paraboloid, I presume, for its primary mirror. No, there's several. It's a segmented mirror, but they're all off-axis.
Yes, they have to be figured off-axis. Yeah.
That's a real tough problem to.
Yeah, but they're smaller, so they're easier to figure than.
How big are they?
They're about 1.4 meters in
Oh, there are lots of 1.4
size.
meters.
Yeah. Mm-hmm. Yeah. Okay. Oh,
What
you.
about the Webb telescope? Where does that fit into the picture?
Well, I haven't talked about space-based telescopes, but the Webb is planned to be launched in 2018. So it would 2018 is about here. So right before these telescopes are supposedly online, the Webb will be launched, and it's primarily an infrared telescope, and it's primarily aimed at cosmology, looking at the faintest objects in the universe. So the ground-based telescope will complement the work from the James Webb Telescope. Yeah. So with these telescopes, it will be possible to take spectra of these very faint objects that are at the limits of observability with the Webb, and it'll be they have enough aperture to take a spectrum. Yeah.
I think in terms of space telescopes, so being able to there, so they can take much longer exposure, so they gain a lot in the amount of sensitivity they have. You know, also the structure, if you figure out how to do it right, can be much lighter weight for a huge big telescope. I just wonder if that's where the really big telescopes are likely to migrate.
Into space?
Yeah.
Oh yeah. Actually, Joe Ritter and I had a discussion about that this afternoon. About there is some people think that as you go to larger and larger apertures, it becomes more attractive from the economic point of view to go into space. And this paper was written over 10 years ago, and so it's not, the conclusions are not valid, but their conclusion at that time was that at roughly about 70 meters, it might become more economical to go into space. But if Jeff can really build his telescope for $1 billion, then this is obviously not true. Yeah. Yeah.
It seems to me that robotics are a necessary part of making space telescopes.
Yeah, robotics are very important for space telescopes. Yeah. Right. Yeah, go ahead, Jeff.
But the telescopes that Alan is talking about are telescopes that are general purpose. They satisfy basically everyone. Because they satisfy everybody because they're there to look at big pieces of the sky, right? NASA, Alan runs a facility for NASA which has many different functions. Right? You saw the back end of this telescope, which is the switch yard for instruments that have to change all the time because there are lots and lots of things that it's doing. If you said, I want to do one thing, I want to go out and I want to look for planets that might, for example, have biomarkers, might have evidence of life, might even have evidence of civilization. That's a telescope that only has to look at a tiny field of view, and it's not a general purpose telescope. So if you control your appetite for doing every problem, then you can do things that you can't do with a big telescope like the TMT or the EELT, the European version of this, right? Or even the Magellan telescope. And that's the reason why this group is going out and looking for $1 billion is not very much money, right? If you look back at this, no, it's not. Look at the big telescopes.
I'll write you a check, Jeff.
The big telescopes, if you inflate their prices to when we're going to build the telescope in 5 years, it's the same price.
It's about this. I say that money is about the price of a B2, a little less.
It's less than the price
Than
of
a
B2,
B2,
right? And compared to one single NASA mission, right? We're at what, about $10 billion now for James Webb, or we will be.
It's about 8, last I saw. Yeah.
And
And this is a telescope which is much
how do you do it? Can you condense Jeff's comment down into one sentence?
Jeff is basically saying that if you build a special purpose telescope, you can build it cheaper with a larger aperture compared to a general purpose telescope. And he's right. Yeah. Yeah.
You mentioned earlier that anything larger than a 10-meter telescope would be too large or too heavy to be supported by its frame. So theoretically, how big are the lenses that are going into these?
How big are the instruments?
Yes.
Oh, for the 30-meter telescope, there's one instrument that's about the size of this room. Yeah.
And maybe I'm thinking old-fashioned, but is there an actual lens in there that?
Yeah, there are some lenses, huge lenses.
And how thick would these lenses be?
The thickness, I'm not sure what the details are, but they're probably 1/10 of the diameter. Yeah, typically. Yeah.
So what is, when you mentioned that going beyond 10 meters would make it too heavy, what was causing the issue with the?
Oh, this was in reference to the Yerkes Observatory telescope. That was a 1 meter refracting telescope. Yeah. So it has a big lens to collect the light rather than a mirror. Yeah.
Is there any sort of multiple refractor lenses for
multiple refractors. I mean, having multiple telescopes on a single mount.
Yeah, or something, or coordinated somehow. I don't know.
Well, there's the
I like to cause confusion, and I see I've succeeded.
well. There is this.
You had your binocular.
Yeah, the binocular telescope is in.
That's obviously not using refractors.
Yeah.
Yeah, we used to have one up on the mountain that had a whole bunch that looked like a Gatling gun.
Yeah, and the Mies Observatory had a spar that had many instruments on it. They can point at the sun, and each instrument might have its own telescope. Yeah.
But it's very hard to make high quality. The quality of glass that you need for that is very high, and it becomes very hard to manufacture, let alone support.
Yeah.
For Titan with the organic material, is it possible that your organic material could form amino acids?
Yeah. The
Large carbon chains?
yeah. The question is whether on Titan the hydrocarbons could form amino acids. Yeah, I think that's very possible, and people have looked for it. They haven't found it yet, but I would be surprised if it wasn't there.
Well, I can't resist it. Has anybody told Exxon it's raining hydrocarbons on Titan? I'm trying not to say that for half an hour.
Well, maybe I should write a letter to them. Although Exxon is history, you have to write to. Yeah, it's if you were life on Titan or if you were living there, the important resource would be oxygen. That's what you'd be looking for. And then you can play with fire. Yeah. Yes?
I mean, is there anything synthetic as opposed to glass for these lenses that people are exploring the possibilities of?
Well, maybe Joe could say something about that, but he's looking into membrane mirrors.
Well, okay, so.
Oh, sorry, let me
there are
re-
reasons why, we can talk after, but there
Yeah.
are.
Let Joe talk into the.
Sure. We can talk afterwards, but there are a lot of reasons why you want to use mirrors and not lenses for telescopes, and Newton taught us that. And so if you have lenses, there are all kinds of aberrations you get, including maybe bending different colors of light, different amounts. And so with a mirror, you only have to worry about one surface, and you reflect the light, and all the colors get reflected the same. Now, are there different materials for mirrors and for lenses? Yes, so different materials have different transmission. So for example, the glass in the window there doesn't let through infrared light that's at 5 microns or something like that. So different materials are used for different transmissive lenses. And then for telescope mirrors, people look at many different types of glass. They're composites. The James Webb Space Telescope is made out of beryllium mirrors. So there are many. Yeah, so it has to do with the stiffness or elastic modulus of the material and how you keep the surface to be a perfect shape within a millionth of an inch and how it's supported. So there's a very large design trade space, and I'd be happy to talk with you about it more.
Yes, go ahead.
For materials, I actually saw something interesting. There's an infrared telescope in space that uses gold to reflect infrared light, since gold is really one of the only good reflectors of infrared. And it was cheap because they made it using just a single layer of gold atoms.
So it's a comment that gold is used in the to coat mirrors because it's very reflective in the infrared. Yeah. Okay. Good. That's right. Well, it's getting kind of late. I'm happy to stick around and answer more questions, but maybe we should break up here.